Hello, 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 everyone, and welcome back to another tutorial. This time we're going to be working with some elevation data and doing some pretty useful geospatial analyses with this type of data. So let's go ahead and get started. Why is elevation data useful and what can we do with it? And some quick definitions out of the gate here. So you might hear the term digital elevation model, or DEM, commonly used to refer to elevation data in GIS. And we can do a lot of stuff with this data. Super useful for visualization. You can make some really pretty, beautiful maps depicting topography and other things. Terrain analysis, right? We can calculate things like slope, aspect, terrain profiles or elevation profiles, like a cross section. Super important for understanding things like water flow, landslides, other risk factors, planning, infrastructure, urban design, golf course building, landscaping, right? So much useful things to do with elevation data. Hydrologic modeling, right? Water flows downhill. We need to know what the topography looks like in order to understand where water is likely to flow, pond, and so on. Lots of other geospatial data analysis involve elevation data as a correction factor or as a classification routine. It's super useful to correct forms of remote sensing data acquired from various instruments and to accurately place them on the right parts of Earth. And then, of course, navigation and outdoor activities, right? If you're going for a backpacking trip in the Sierra, you probably want to know how much mountain or how many feet of mountain you are going to climb and over what period of time and distance. Also, like low flying planes, right? Like you probably want a pretty good sense of how high the mountains are and how high you need to fly to be sure that you're going to make it over the mountain pass. So, this data is very useful for lots of things and is used widely across a number of sectors. Here is a nice example of some elevation data for Mars. And here, the blue colors show lower elevations, and the red and brown and white colors show higher elevations. So this is really cool. You can see lots of craters, you can see some mountains, and just quite easy on the eyes to look at as well. So, quick clarification. There are kind of two types of DEMs or digital elevation models. There's what's called a DTM, a digital terrain model, and there's a DSM, a digital surface model. The DTM, the terrain model, contains only information about the surface of the land. So no buildings, no vegetation, no cars, no people, nothing that occupies space above the surface. We are just interested in the land surface and the topography of that. Whereas a digital surface model does, in fact, factor in the elevation changes associated with things like vegetation, buildings, humans, cars, anything else that's present on top of the land surface. That's the real difference here. That would be included in the digital surface model, whereas a terrain model is exclusively the land surface. So this is a tutorial. You should have all of the background data that you need about rasters and working with rasters in order to successfully perform this tutorial. So go ahead and download the SPR elevation.tiff file from Canvas and open it in QGIS and follow along with my tutorial here. So I'm gonna X out of this slideshow. I'm gonna fire up QGIS and I'm gonna download those files from Canvas. So pulling up my Canvas right here, downloading my elevation data, Let's minimize that for now. Opening up QGIS. Let me see if I can load up the elevation data that I just downloaded. So I'm going to go to my browser panel. And a quick reminder, if you've lost your browser panel, if you've lost your layers panels, you can go to View, Panels, Layers. You can also go to View, Panels, Browser. You can also get the processing toolbox back and quick map services back should you need it by going to View, Panels, Processing Toolbox, and also View, Panels, Search QMS, which is Quick Map Services, which is our base maps. So we've got all of our panels. We're ready to go in GIS. Let's go and get the elevation data that we just downloaded. I am going to go get it from my downloads directory. I think it's called SPR elevation.tif. Great. Let's load that up. Looks like that. Seems reasonable. I'm going to add a base map to add some context. There you go. This area might look familiar. It's our old friend Swanton Ranch. So, great. We've got our QGIS open. We've got our SPR elevation file loaded. We are going to do what we always do and check the projection information, the coordinate reference information associated with this data to see what units it's in, right? We see some values here, 1,803, negative 1.48. We might have some guesses about what the units are based on where we're at and how high things are in that area, but let's just check to be sure. So we can open up the properties menu by right-clicking the layer, clicking properties, and then if you go to information here, scroll down a little bit, you will see the coordinate reference system is in NAD 83, California Zone 3. That looks like a state plane system. You will see the units are in feet. So these mean feet above sea level, right? The reference elevation to which all these values are relative is sea level. So the tallest pixel in this image is about 1,803 feet, closer to 1,804 feet above sea level. Great. So we can do lots of pretty interesting stuff with this data. The first thing we're going to do is make some contour lines. We can do that by going to Raster Extraction Contour. This menu should pop open. And see if you can figure out what this is telling us. So this is asking, what is the interval between our contour lines? Essentially, how much space in feet are we going to add between each line that we create? You probably are familiar with contour lines from the maps that we looked at in the first couple of weeks of this class, but this all looks good. I'm going to change this to a little bigger value, something like 30 feet to speed up the processing. I'm going to click Run, and voila, there we have some contour lines. Very cool. They seem to mirror the elevation that we have nicely. You can see that they do, in fact, kind of hug the same color scheme and topography in the raster data. And keep in mind, these contour lines, they're lines, right? They're a vector data set. So they're we've converted from raster data to vector data. In fact, we've converted to vector lines. And you can, just like other vector data sets, you can inspect the features by clicking and highlighting and checking out the Identify Results panel. You can click the Identify Features button up here to do that. And you will see for each line, there is a value of elevations. And each point on this line essentially has the same elevation. That's what the contour tool does. It connects the same elevations with lines. So for instance, up here, this is a peak, 750 feet, and that's kind of like the summit of this little hill. And then with each line, with each successive line, we're going down 30 feet in elevation. So if I highlight this one, we're at 720 feet. And what do you think the next one will be? 690, right? Because we set our contour interval as 30 meters. So this is super for visualization and can also be really useful for doing geospatial analyses. And I think stay tuned for Project 4, where we will be using lots of this stuff. So great. That was contours. Let us now do the next processing step, which is deriving from elevation data slope, right? So think about how we could get slope from elevation data. What mathematical operation might we conduct or perform on the elevation data in order to derive slope, right? And a helpful way to think about this is, how do we determine the slope of a line, right? It's, x1 minus x2 over y1 minus y2. So you take the difference in the x and the y coordinates, right? Rise over run. Essentially, we do the same thing in 2 dimensions here. We take the spatial derivative of the elevation data in order to calculate the slope. We can do that super easily. So we just go to raster, analysis, slope. Keep in mind, you can also access all of these handy tools from the processing toolbox right there. So selecting elevation as our input layer. Note that you can express slope as either percent or degrees, right? 100% slope would be 90 degrees, like fully vertical. We're just gonna stick to degrees here. There's pretty easy ways to convert to and from both, but let's go ahead and click run. And look at that. Isn't that beautiful? These are our slope data, right? And if we look at the color map here, you can see that it goes from about slopes of basically 0, like totally flat, to slopes of about 80 degrees, pretty steep. And that kind of makes sense with our understanding of the shoreline right here, where we might have some steep cliffs that drop right into the ocean. We have those near Avila Beach and Montaña de Oro, so we definitely have similar ones up by Swanton Ranch as well. And here they are, 80 degrees slope almost. And again, if you click on the identify tool and then click on a pixel, you will get the slope value at that pixel. So here we've got pretty big slopes, 66 degrees, 63, 54. And then here in the river valleys, we've got very flat ground, 0.7 degrees, 0.2, 7 degrees. So pretty big differences in slope just in this area. Now, let's compare the slope to our contours data. So I've just dragged the contour lines up top. And what do we notice? And this makes total sense if we think about it a little bit, but they look pretty aligned, right? That makes tons of sense too, because where the contour lines are close together, that's essentially a big change in elevation over a short distance or a high slope, right? So take this area, for example, we've got, very close together contour lines, 510 elevation all the way up to 600 and even more probably, because these are 30 feet intervals, and we've got lots of lines, so that's at least a few hundred feet of elevation change. And if we look at the slope and click identify, we've got pretty, significant slopes here of 30, 40 degrees. So makes a lot of sense that we would have high slopes in areas where contour lines are bunched up together. Essentially, those are the same phenomenon being shown in different ways. So great, building our intuition of slope, topography, and elevation. Let us experiment with some colorization here really quickly, because that's always fun. So right click on the slope layer, go to symbology, select single band pseudo color, and pick some different color ramps and classification schemes here. So I like kind of this rocket one, kind of shows steep slopes as red and shallow slopes as black, but there's all kinds of beautiful visualizations that one could make using these tools. So pick one that suits you, and we will chug along. So be mindful of the units in slope. When you're calculating contours, be mindful of your contour interval, right? The distance between each line that you create. And can we think really quick of a few areas where this would be pretty useful, right? What are some applications where we would want to know the slope, the contours, the elevation, the changes in these values for doing some real projects? And encourage you to pause here, ponder that question that I just posed, and then unpause for some answers that I'm going to give. And I suspect that you probably thought of some good ones because there are many. So for instance, logging. We can't operate the heavy equipment to do logging in slopes over 20 degrees. So understanding the slopes before we take those heavy machines out to the forest, probably a good idea. Construction, right? We can't build stuff on high slopes. We might need to do leveling, but how much earth do we need to move? How much slope do we need to flatten, right? Those are questions we can answer using digital elevation models. And hydrology, right? Where is the water going to pond and collect? Water obviously doesn't pond on high slopes, it flows downhill. So understanding the slope and the topographic characteristics of an area are important and very ascertainable using this kind of analysis. So, okay, a little thought experiment. Let's say we want to separate areas that are less than 20 degrees and greater than 20 degrees in slope, right? And this is pretty practical. There's several reasons why we might want to do this. Well, let's go back to QGIS and see if we can do that. Now, we can do this in the symbology quite easily. So if we open up the layer properties, go over to symbology, change the mode to equal interval, and change the number of classes to 2, and essentially set this value right here to 25. What we've done now is essentially split these data into 2 color categories, and I'm going to label them 0 to 25 degrees and 25 degrees plus. So for the lower slopes, let's make them green. Maybe we are comfortable building on them. And for the higher slopes, let's make them red. Maybe we want to avoid them. And if we click apply, there we go. High slopes shown in red, lower slopes shown in green, and we've got a pretty cool looking visualization here. But let's say we actually want to go a step further and calculate how much area consists of high versus low slopes, and we're going to use that 25 degrees as perhaps an arbitrary cutoff. Well, one way that we can perform this reclassification is with the tool called Reclassify. Yes, it's under raster analysis. And you want the tool called Reclassify by Table. So I've opened that up. I believe it's also up here, raster analysis. Oh, no, it's not there. We need to go into the processing toolbox to get there. And as a reminder, if you don't see the processing toolbox, you can get it from View, Panels, Processing Toolbox. Click that on and it should be good to go. Search for Reclassify and select this tool, Reclassify by Table. Put in the slope as the raster layer. Open up the Reclassification Table dialog by clicking the three dots. Add 2 rows. We want a maximum of 25 degrees, and we're going to call these zeros. And then let me back up. We want to group slopes between 0 and 25 degrees together, and we want to group slopes of 25 or more degrees together. So what I'm putting into this reclassification table is I'm telling this tool any slope, any value in this layer between 0 and 25, give it a new value of 0. And any slope between 25 and 90 degrees, give it a new value of 1. And it's going to create a new raster layer with only those values and with these ranges from this layer grouped into those values. So essentially there will be a 1 anywhere where we have a steep slope, aka those red areas, and there will be a 0 anywhere where we have a shallow slope, right? So I'm going to go ahead and click OK. I'm going to click Run. And there you have it. We have now classified our slope raster into a few different classes, right? The steep slopes and the shallow slopes. Great. Now, in order to calculate the areas of both of those, you could convert this to a vector and then do some basic summing statistics. You could also sum up all of the zeros, sum up all of the ones in this raster. There are other ways to calculate those areas that we've already covered, so I'm not going to go through them here today. But if you need a refresher, you can Google something like calculate areas for raster classes or similar, and you should get a good answer. So, okay, great. We have just covered slopes, reclassifying slopes. Now we're going to work with aspect data. So I imagine you folks know what aspect is. It's essentially which direction does the land face, right? Does it face north, south, east, or west? And we have a handy tool called Aspect that we can use to figure that out. So search for Aspect in the processing toolbox. You can also go to Raster Analysis Aspect. Let's pop that open. And what do you think the input layer is going to be? Well, it's going to be, well, let me let you think about it for a second. So pause and ponder. Do we want the slope or do we want the elevation? Right? We actually want the elevation because that's actually going to tell us more, you know, which direction is this pixel facing? And we need to know some information about the other neighboring pixels, right, in order to figure that out. But input the elevation. Notice that there's some other options here. We don't need to worry about any of those for now. And go ahead and click run. Interesting. So we have a pretty cool looking new raster layer called aspect. I'm gonna just click off and collapse all of the others so we can focus on it. And you'll see that we have values in between 0 and 360 in our new raster layer. Now, when I see 360, I automatically think of the number of degrees in a circle, right? And if you can use your imagination a little bit, you might be able to figure out how each of these values corresponds to a different direction. Think about, and in order to visualize that, think about this unit circle that shows each of the cardinal directions and the corresponding values in units of what are called azimuth. So this map that we just created is showing essentially the orientation of each pixel in degrees, with 0 and 360 being true north, 90 being east, 180 being south, and 270 being west, right? It's exactly the units in this circle right here. And so if we wanted to colorize each pixel now by its cardinal direction, if we wanted to colorize this aspect data now by the cardinal direction which the pixel faces, which as a quick reminder are shown here in the unit circle, we can just alter the layer symbology to show that. So let's go to properties, symbology, single band pseudo color. We want an equal interval mode, and we want 5 classes. Now, take a second and think about what values we want to put in each of these classes. So we have values of 0 to 360, and we know from the unit circle that north is basically 350 to 45, 315 rather, to 45. East is about 45 to 135. South is 135 to 225 degrees. West, 225 to 315. And that's it. So how do we get that into here? Well, I'm going to put in 45 as our first kind of threshold. Second one was 135. Next one, 225. And the last one, 360. One thing we got to do, though, keep in mind the values between, we got to set 315 as the last one. Our values between 315 and 360 are the same as our 0 to 45 directions, right? That's both facing north, 315 to 360 and 0 to 45. So we're going to color both of those the same color. All right, let's make them black. Great. So now we're set, right? What are we telling this computer to do in terms of the symbology? Values between 0 and 45. We're going to make them black to denote north. 45 to 135. We're going to make them this dark blue, and those are going to be east. 135 to 225. They're going to be this kind of lighter blue color, and they're going to be south facing. 225 to 315, west facing, this color, and 315 to 360 are going to be black and north facing. So I'm going to click apply. If I slide over, you can see that my map has updated, and these colors now show the cardinal directions. And we can change these, right, to be perhaps more visually appealing or to show contrasts that we want to show, but feel pretty confident that we are accurately rendering these cardinal directions based on our aspect data. Great. I want to show one more thing. And it's similar to the aspect data that we've been working with, but I'm going to show it on the elevation layer. So I've just dragged it to the top here. And it's actually just a visualization technique, a pretty simple visualization. So right click, go to properties, change the render type from single band pseudocolor to hillshade. And maybe click apply and see what happens. Now, doesn't that look like the aspect data that we just were working with? It sure does to me. What this hillshade visualization is doing is saying, okay, let's pretend that the sun is at a certain point in the sky and is illuminating this landscape. And based on the position of the sun, where would the shadows fall? So this little clicky circle right here is showing where you want the sunshine to be coming from. And the coordinates are the same azimuth degrees as we were just working with in our aspect data. So a value of 360 means the sun is shining from the north. So let's just, 359, close enough. Let's go ahead and set the azimuth to 359, click apply. And you'll notice things are different. The shadows are now facing south. What if we shine the light from the east? I think the shadows will probably face west. Indeed, they changed, right? What if I flip this to a west, like a setting sun? We can observe these shadows change. Look at that. You see way more shadows here and not so many here, which makes a lot of sense given that the sun would be shining from this part of the screen. So hillshade, a very powerful visualization tool that I recommend getting comfortable with. And I believe between elevation, slope, contours, aspect, hillshade, you have many of the foundational GIS tools that you need to conduct topographic analysis and begin solving real problems. Thanks for your attention.